Einstein never abandoned the November tensor, a challenge to the standard narrative Galeno-Einstein. In 1912, in his Zurich notebook, Einstein employed unimodular transformations where the square root of minus g equals 1. Thus, the logarithm of the square root of minus g approaches 0. This leaves the Ricci tensor with the second and third terms in the equation. These two terms constitute Einstein's gravitational tensor. What remained, two specific terms, inspired Einstein to define what he believed could be a gravitational tensor. Historians later call this construct the November tensor. It marked an early promising step in Einstein's path toward a generally covariant theory. Einstein noticed that under unimodular transformations and the harmonic condition, certain terms in the Ricci tensor simplified dramatically. This led him to isolate a second-order differential term, what I refer to in my book Einstein's Legacy and here as the Laplacian-like term. While it resembles the Laplacian operator from Newtonian gravity, Einstein's initial treatment revealed critical differences. Still, this term gave him hope that the equations could reduce to the familiar Poisson equation in the weak field limit. This is what I call in my book Einstein's Legacy the November coupling term. It appears in Einstein's truncated version of the November tensor in Einstein's 1912 Zurich notebook. This term involves a product of first derivatives of the metric tensor weighted by the background coefficients. It captures nonlinear interactions in the gravitational field and is structurally very similar to a term that reappears in the Einstein-Grossman 1913 Entwurf field equations. The mathematical form reflects an early glimpse of what we now recognize as the nonlinearity of gravity, something Einstein was struggling to include into his field equations. This term shows that Einstein's thinking continued to orbit around the same structural features. This term, taken from the 1913 Entwurf field equations, structurally mirrors the earlier November coupling term. Although Einstein had moved on from the Ricci tensor, he recreated a nonlinear term of a similar form using metric derivatives and background coefficients. This continuity reveals that Einstein didn't abandon the November tensor entirely. He carried forward its structural logic into the next framework. The resemblance between this expression and the November coupling term illustrates Einstein's evolving yet persistent intuition about how gravity should self-interact through nonlinear terms. I have traced a through line from Einstein's engagement with the November tensor to the final form of the 1913 Entwurf field equations, revealing an intellectual continuity that is often overlooked or assumed to be broken. I have shown that Einstein didn't fully abandon the November tensor. I have shown that Einstein didn't fully abandon the November tensor even when he shifted theoretical frameworks. Instead, key structural elements such as what I call the November coupling term subtly reappear in later formulations like the 1913 Entwurf field equations. This insight cuts against the common narrative of a clean break between the Ricci tensor and the 1913 Entwurf field equations. I am showing in my book Einstein's Legacy that Einstein's mathematical imagination carried these form, the November coupling term and the nonlinear terms across shifting frameworks, even as his physical interpretation evolved. Thank you for watching this presentation.